Hi, so in the last video, we learned about the rules for load shear bending graphic approach, and now it's time to apply it. So the first example, we will be using the simply load beam with concentrate load in the middle. So here we go, load shear bending diagram, graphic approach, example 1. If you still remember, in that video, we look at simply supported beam with concentrated load in the middle, and we calculated reaction support is P/2 on each side due to symmetry. And our goal for this one is to directly draw load shear bending diagram without making any cut, without any solving equilibrium equation, without any extra free body diagram, just directly using the rule for graphical approach. All right, so let's try it. So directly jump into our tier. So the first tier is our load. Okay, for our load, like we said, it's basically your FBD. We just copy that down right here. For shear, all right, I hope at this point you will pause the video and take the note you had for the last time in terms of the rule for graphic approach and have that by your side so you can follow along to apply them into this problem. Remember the first rule we have over there is if you have a concentrated load, the shear goes the same direction as the load. So we have 3 concentrated load right here. The first one, the shear diagram is going to go the same direction as the load. So at this load, it's going upward. So shear is going to go jump up, upward. How much? Exactly the load concentration, P/2. Then let's continue. So that's the first point. And if you move along this direction, you realize there's no other force or moment in between. So this shear is going to continue to stay constant as its horizontal line as P/2 until you meet the second concentrated load, P. So when you have a concentrated load, rule number 1, the shear gonna go the same direction as the concentrated load. So this is going downward. From where? From P/2 downward to downward how much? P. So it's P/2 minus P, going down that much, and that will give us negative P/2. Okay. Then we continue to go after. There's no other force, so it's going to be continuous staying constant until we meet our third concentrated load. From negative P/2, we're going to jump same direction upward. How much? P/2, this value. So from negative P/2, jump up P/2, that will give us back to 0. That's our shear. Pretty interesting, right? I mean, without doing any free body diagram, without any equilibrium equation, you got the shear profile for this beam. Pretty handy. Now let's look at the last tier, which is our bending. For our bending, we're going to go back our rule. Let's take a look. Rule number 2 does not apply for this one because there's no distributed load. However, rule number 3 and rule number 4 will apply. And from this, you have already figured out the moment, the bottom tier, is basically the integration of the shear. So if you already have a shear profile, the area underneath the shear is going to give us our bending. That's why we call this a graphical approach. And be aware, this area has positive and negative. If it's above, it's positive. Below, it's negative. So bear those rules in mind. We're going to apply that. So area underneath this shear diagram is going to give us our bending. If I were to integrate this entire area, that gives us the bending at this point, okay? Because I'm integrating from first half of it. So now let's think about what's going to be the area of this entire rectangle. The length is L over 2. The height right here is P over 2. So the area will be PL over 4. And this area is indeed above our x-axis. So that means it's positive value. Okay. So now let's translate this into our bending diagram. For our bending, it's area underneath the shear give us the bending. So if we were to integrate from this entire rectangle, you got this area. So that's going to give us this value right here. That's our P. That's PL over 4. But think about it. If I were just trying to integrate this area, right here, what would be the value? That would be somewhere in between those two values, right? So thinking about this is a little quick recap our calculus knowledge. When you have y as a constant value, for this example, which is P over 2. If we were trying to integrate your y dx, we will get P over 2x. So if you have a constant value, when you integrate this constant line, that will give us a first power. Now let's think about another scenario, which does not apply for this problem. However, you will see it very soon. When this y have not a constant value, it's going to be x. Constant value, that's x power of 0, right? You know. Here I mean the power is 0. And if, however, for second scenario, if y is equal to x, what is going to be your integration of y? It's going to give us power of 2. Then let's continue. If y is already power of 2, when you integrate of y, we will get power of 3. Okay? So knowing this, go back to this particular problem, which applies to our scenario number 1, because this shear we're about to integrate to get bending. This shear is a constant value, so we're going to get a power of 1, which is linear. Then, knowing this endpoint is PL over 4, after you integrate this entire highlighted area, we know when you start integrating here, that's going to be 0, right? When you start to integrate more and more, this value increases linearly as a power of 1 to this value. Okay? So now, let's look at second half. What's going to be the area underneath this curve? First of all, this is below. Then that's going to be negative. And what is the area of this rectangle will be this length which is L over 2, then times the height, P over 2. And here I don't put a negative P over 2 because I'm just worried about the height magnitude. And here I already defined as negative since it's below. So that's going to give us negative PL over 4. So what does that mean is when I have integrated this first half gets to P over 4. And then I'm going to start integrate this second half to get bending. However, the second half is going to basically, I'm adding negative value along the way, right? Because it's below. So until I integrate this entire negative rectangle area, that's going to give minus that much, PL over 4. So if I start with PL over 4 and I'm integrate adding more negative value along the way until I'm adding the whole rectangle area of PL over 4, that gives us 0. This point is 0, okay? So that how do we get this? It's P over 4 from this point minus this area, you got it. So that will give us 0. Then I actually took the liberty to already draw this linear line. Because why? Because this shear, it's this value right here as negative P over 2, which is a constant value. When you integrate that, you're going to get power of 1, so which is a linear. That's how we got our bending. Okay? So this is our first encounter of using graphic approach to solve low shear bending diagram. And we're using basic calculus knowledge, the area underneath the curve, adding a few new rules here, and we got our first low shear bending diagram. So next video we will look at using example 2 from an analytical approach and to apply this graphical rules again. All right, until then, see you next time.